fridges. They keep things cold. We like them. But did you know there are some fridges that can go to the coldest temperature physically possible? And that until now, we've never actually been able to see how they work? Well, buckle up, because we're going on an adventure of the best kind, the fridge kind. And for that, we need to go somewhere very special. What happens here at the ISIS neutron and muon source?
Well, mainly it's a particle accelerator, and it's a facility for users. So scientists from all over the world come to use the equipment here to do whatever their own research and interests are.
ISIS is the UK's only neutron and muon source. People come from all around the world to study materials and matter of all sorts. Anything you can think of, you can study it pretty much with neutrons and muons.
What is a neutron?
Good question. So a neutron is a subatomic particle. It's found in the nucleus of atoms, along with the protons, which is another subatomic particle. And if you add electrons as well, then those three together make up all of the atoms of everything that we have around us. But it doesn't have an electronic charge, so the protons are positive and the electrons are negative, but the neutrons are neutral, which is why they're called neutrons.
How do you make neutrons here at ISIS?
So here at ISIS, we make neutrons with a particle accelerator. The useful thing about something that is positively or negatively charged is that you can use electromagnetic fields to control those particles. A neutral particle isn't so easy to control. To begin with, we start with H- ions. First step in that is a LINAC. That's a shortened term for a linear accelerator. We need to then accelerate them to give them energy and to make them go faster. So the next step after the linear accelerator is to inject it into the synchrotron. First it goes through a thin film and it strips the electrons off, so you're just left with a proton. We add bending magnets that bend the beam and keep it on a circular path. You can accelerate it many times. Every time it goes round, you give it another little kick. So they get up to 84% of the speed of light.
How then do we get neutrons from these protons?
Neutrons are all around us, but they're just difficult to liberate. But if you hit metal really hard with a beam of protons, it releases energy by releasing neutrons.
We send those towards a tungsten target. The interaction of those really high energy protons with that target causes a really bright flash of neutrons.
Where do the neutrons go?
Basically everywhere. They come out in a big bright flash in all directions. There's a reflector around it which helps to direct the neutrons kind of outwards towards the instruments. Then each instrument is at the end of what we call a guide, a neutron guide, which is basically a long tube which will help to reflect the neutrons down them.
So, what is IMAT?
So IMAT is the imaging beamline here at ISIS. If you've ever been for an X-ray at a hospital, it's a bit like that, but instead of using X-rays, we use neutrons. It comes through whatever you put here in the middle. This is the sample stage, and then right here there is a very special camera which can see the neutrons. We essentially can take pictures through a sample using neutrons instead of using light. At the very top there you can see the camera itself, and that still detects light. But what we have at the front here is a special screen, and each time a neutron interacts with that screen, it causes a small flash of light, and that allows us to go from a beam of neutrons into seeing a picture like you would expect.
Why are neutrons in particular useful?
So we already use loads of different techniques to study materials and matter. Neutrons are really good at looking at lighter atoms and interacting with particular elements. So things that you can't look at with X-rays or lasers, you can look at with neutrons instead.
Would you let me put a minifigure in the IMAT?
100%.
Okay, let's do it.
Let's do it.
Well, that surprisingly worked. Time for something a little bit bigger. What is a dilution refrigerator?
A dilution refrigerator is a device that uses a mixture of helium-3 and helium-4 to overcome the barriers of cooling that you experience if you're using just one of those fluids. So here we use the dilution fridges in combination with some other cryogenic equipment like cryostats and superconducting magnets to provide the lowest temperature sample environment for the samples that come in to be studied by the neutron source. So you can think of temperature as basically a form of noise, which is covering up the fine detail of the science that's happening within the sample that's been brought by the scientists. So if you remove all that noise by lowering the temperature, the perhaps quantum behavior of the sample can be brought to life. You can actually see it.
So fundamentally, dilution refrigerator is the same kind of refrigeration device as a domestic fridge or any cryostats we are using, where you are essentially evaporating a liquid. So let's say if you have a liquid in container, and if you start evacuate a vapor above the liquid, the temperature of the liquid goes down. Interesting bit about dilution fridge, it works upside down. In mixing chamber we have two liquids essentially, helium-4 isotope liquid and helium-3 isotope liquid.
Helium-3 is an isotope of helium-4, so it's essentially the same, but it's missing a neutron. Below about a Kelvin, a mixture of helium-3 and helium-4 will undergo a phase separation, so it'll become helium-3 and helium-4.
Is the separation simply because helium-3 is lighter and it wants to float on top?
It floats on top because it's lighter. The separation is due to quantum mechanical effects. So you can force helium-3 atoms to cross the phase boundary between the helium-3 and helium-4. Doing that crossing requires energy. Energy has to come from somewhere, it comes from the local environment, that's where the cooling happens. Here we get to 20 millikelvin fairly routinely.
What made you decide to image a dilution refrigerator in the IMAT? Can you remember?
No. Aside from it being interesting to do, it hadn't been seen before. There were lots of illustrations in books and supporting measurements, but there's nothing quite as striking as a picture or a video.
Why is it difficult to see inside a dilution refrigerator?
Cryogenic systems are quite often very well contained. They have to be, because even visible light is a heat source, so you want to shield against it. What makes neutrons useful is that neutrons, on the whole, will pass through metal quite easily. If you imaged a fridge with an X-ray source, you would just see a silhouetted outline of the cryostat, actually.
this is the Neutron image.
It is. This is what we see. This is our dilution refrigerator. The cold helium mixture comes in and then hits hot parts of the fridge, boils, and then gets thrown back out again. At this particular point, the mixing chamber is completely full of liquid, and as we're continuing to pump on the liquid, the temperature of that liquid is reducing. Before too long, it will get cold enough that the lighter helium-3 will want to float on top of the helium-4, which is the necessary stage before dilution refrigeration can start.
What modifications have you made to the mixing chamber to get this experiment to work?
Right, okay, so we've added this like insert into the mixing chamber, and we've put in a little slit so that the helium-3 can be seen by the neutrons.
So what we're looking at here is our mixing chamber again, back in the black and white colour scale. This is the phase boundary that I talked about before. So here is our helium-4 on the bottom and helium-3 on the top. Dilution refrigeration would not work at all without this effect, and we have been able to see for the first time what is actually happening during that process.
How did you feel seeing the results come through for this experiment?
Oh, elated, because it means all of the effort and thinking and calculating is worthwhile, and you got it right. Yeah, it's a really great feeling.
It was a very good moment. It was a lot of joy. It was like, wow. yeah. Amazing. And completely unexpected.
Very relieved. There was a lot of work building up to this, and we're very pleased to be able to get a good set of results that will get us a good scientific paper.
I guess you could say that is one cool experiment. So, how big are these tungsten targets?
I don't know.
Okay.
Yeah, I'll try not to whisper.
Yeah, fine.
Project. Brian blesses.
Project, that's it,
Channel
yeah.
Brian blesses.
What brought dilution refrigerators to this facility?
So dilution fridges have quite a bit of history at Harwell. They started the development here back in the 60s.
Hi.
No,
No, it's okay.
3-2 now or 3-2-1 now?
It's on now.
Now?
Okay. Right, everyone look at the screen and get ready. So slide please, Alex. Now!
That's really good. Right, now we'll tidy up that.